events this month. No big surprises going on. Mercury has disappeared from the evening sky by now, headed through inferior conjunction. Venus, of course, you can't miss it in the morning sky. It was rather pretty when I was pulling out, headed for the mountain this morning. Mars, morning sky, still lowish, but not bad. Jupiter now starts rising in the late evening sky. It's now well up. Saturn, of course, morning sky. Uranus and Neptune easily, nicely positioned in the evening sky as soon as the sun's down. Nothing hugely exciting going on astronomy-wise in the sky. A couple conjunctions is about it. Full moon, 23rd. New moon was just this weekend. Who got out and observed?
I was on Mauna Kea. My back, well, the mountain, and I wonder how many people saw the fairly close conjunction of Venus and Saturn.
Yeah, you said that the sent photo, but I didn't get up that morning. Just the photo, but not the real thing.
Well, it was quite nice.
Yeah, they were close. What, a half degree or so?
Yeah, a little over.
Both in the same eyepiece field, anyway.
Yep.
Yeah, I got out, went out Saturday night, spent till midnight up on the side of Mauna Kea, just bouncing through galaxies south of Orion. I got some good dark sky time. Can't complain. Okay, Moon and Jupiter, 4 degrees, the usual sort of thing that happens every month or so when Jupiter's high in the sky. Nice conjunction on February 5th of the Moon, Mercury, and Venus, all in a nice little 6-degree triangle.
That would be nice.
So February 5th.
Yeah.
So other than that, not much going on. No meteor showers, no eclipses. I was going to talk briefly, run down a few things that are going on this year. Let me just close my notes. Just give you guys a quick heads up on what's going on this year, during this year. Just take me a moment here. Maybe. Okay. So there's a few interesting things going on this year. First of all, we do have a Mars transit going on this year. It's not a bad one. Of course, Mars can vary between, 14 to 25 arc minutes in apparent size.
Right,
So it can
right.
almost double in size depending on just how good the opposition is, whether Earth is all the way at perihelion and Mars is at aphelion. Can vary how big it is in the telescope by almost twice the size. So this year it's getting bigger. We're kind of coming back into phase. So it's 18.6 arc seconds.
That's good.
So it's not bad. Of course, it can vary between 14 and 25. The next opposition 2 years from now will be very good. It'll be a full opposition close to the maximum size. So the really good Mars opposition is still 2 years out. But this one isn't bad. 18.6. May 22nd is opposition. So
Excellent.
obviously a month either side of that is prime time for Mars viewing. Let's see. Jupiter will see opposition on March 7th this year, and Saturn won't go through opposition till June 2nd. Let's see, what else we got? Eclipses. We're going to have the total, which everyone was talking about here, goes across the north end of Indonesia and out into the Pacific. It actually comes through the Hawaiian Islands, the center line of totality. Unfortunately, that's the loose definition of Hawaiian Islands that includes Midway. So yeah, the center line of totality passes just south of Midway. So it's still a few hundred miles from here, which means it'll be a deep partial here in the islands. We get, I think on the Big Island, we get something like 55%. Yeah, 55% for Hilo, 67% in Kauai for Lihui.
Well, that's really cool. What time of the day does it occur?
It's an evening eclipse. So maximum eclipse is 5:30 eclipses this year. We have a couple penumbral eclipses, minor. I mean, you probably have to have an instrument to tell that the moon changes in brightness. And there's a second solar eclipse. It's an annular, but it happens over the Indian Ocean and Africa. So basically one eclipse for the year, the partial in March.
Except for us who are on the cruise ship.
Yes, for those willing to travel, you can change that. Okay, let's see. The best set of conjunctions for the year probably will start in mid-August to mid-September, occurring in the sunset. Mercury, Venus, and Jupiter will all dance pretty close together. Of course, the moon will swing through the trio on a couple occasions over that month. Let's see. I got the pass between Saturn and Venus on January 8th. Yeah, Venus and Jupiter will pass within 12 minutes of each other, August 27th.
Woo!
And
That would be really good.
yeah. And there's one close pass of the moon and Jupiter on August 5th, almost an occultation here, 40 minutes. Just 10 minutes. Jupiter's just 10 minutes off the limit of the moon. Of course, we've still got Comet C 2013 US 10 Catalina, a nice telescopic object in the morning sky right now. We've got we can slide on that, and there we go. It's actually going to swing right through the North Polar region, not very far from the North Pole at the end of the month. So very nicely placed for observing for Northern Hemisphere observers. Meteor showers, not a good year for meteor showers. Unfortunately, the moon is troubling. The quadrantids were probably in fact, just a week ago, were probably our best meteor shower of the year.
They were nice.
Yeah, so there'll be a little slot of time between the peak of the Perseids and moonrise, where the waxing give us moonrises, or sets, I guess. So maybe if you time it right, you'll get at least a couple hours of Perseid watching.
Can't see the constellations where it's doing that loop-de-loop.
Auriga and Perseus.
What was it?
Auriga and Perseus.
Okay, nothing really familiar.
Yeah. Well, they're familiar to me. I hope they're familiar to you.
Auriga should be northern sky, right?
Yes, very northern sky. Well, you can see
Very
it
northern,
yeah.
passes within like 20 degrees of the North Pole
It's
there.
circumpolar.
That's Auriga down there?
Yeah,
with the
that
bright
one
star from
bottom
down there.
center.
The red in it.
Bottom
inside
center,
the
yeah,
green.
that's bottom center.
Part of the Auriga, okay.
That's Auriga.
So that's easy to find.
Yep, right next to Capella. By that time, it'll have dimmed substantially, so it'll be strictly a telescopic.
What's the date on that?
Well, the question is, at the end of the month, it'll be passing by the pole, and then it won't get into the loop-de-loops until March and April, and for the rest of the year, it'll be in that loop. So,
End of March, early April.
yeah, then enters that loop, and then spends the rest of the year making that one loop, that first loop. Okay. I think that covers the highlights of the year. So if anyone wants to plan ahead, that's about it for interesting astro events for the year.
How about night with these?
That's a little different. Okay. What do we got here? There we go. So I'm gonna hit club business for a minute. Lapa Hoi Hoi Charter School. Who's joining me on Friday night for Lapa Hoi Hoi? Excellent. Okay. We do have a latecomer sneaking in. Sneaking in and sitting in the back. Hoping the instructor doesn't notice.
Now, that's the same one we did before, right? It's the same school, isn't it?
No, we've done Pa'ilo out there before. Lapa Hoi Hoi Charter School is, in Lapa Hoi Hoi proper. So I suppose I ought to send out good directions to
Yeah,
exactly
because
where I need to
I
be.
went to the one before, not the,
Right.
yeah, that would be very helpful.
Okay, I'll try to send out good directions before we go.
Good.
Is that where the old tsunami, is it? Years ago?
Well, that's Lapa Hoi Hoi, if that's what you mean.
Yeah,
You know
No,
where Lapa Hoi
this is
Hoi
up on
Park
the,
is.
this is up on the hill,
Up on the
right?
hill, yeah.
Ah, that's on the hill.
But right there. I mean, okay, so we'll have, I understand several other telescopes are joining us from the Hilo side, so it should actually be quite the evening out there.
Good.
I don't know if we'll have enough audience for the telescopes. We'll see how well they, the school population responds and shows up. Let's
What's
see.
NGC 891 you showed us, you sent us a picture of.
Yeah, that's, in Andromeda, it's, Edge-on Galaxy.
It's what?
It's an Edge-on Galaxy.
Oh,
in
Edge on,
Andromeda.
but it was very small.
Yeah, well, that's because of the way I took the picture. It's actually quite large.
How far away?
I think it's about 12 light years.
Okay, so it's, you took the big scope.
No, actually, well, it's pretty faint, but that was through the mean 16 at the biz.
Oh,
Okay, so I think Evening with Astronomers has been adequately arranged by Mr. Erickson. Thank you, sir.
Thank you.
Thank
you're
you.
the best.
No, we've got a good staff of scopes available for each of the evenings, so I think we're in good
Yeah,
shape.
March is a little tricky when Whitmire in Indonesia.
I'll cover for you.
Yeah, we'll be in Indonesia. Did I mention Indonesia? Did I mention Tokyo? Just in
Yes.
case you didn't.
Okay, let's see, what other bits of club business do we have? Cliff, anything?
Well, I've been talking a lot to Joe, and we've started, which is incredible, of getting amateurs back up at the biz for New Moon.
Yeah, they were driven off by the protest for a year.
Yeah, and, of course, I've been the only one from here, but the Hilo people have been up there, and it's been real good. I've been talking to Joe about it. Joe is willing, knowing ahead of time, to keep the microwave hot water out, and, would love to see us come up. And I was thinking maybe if people are interested, on the new moon of, February, maybe people would like to go up to the biz again.
Yeah, I'm working up a schedule for club nights and Konaku nights for the biz.
Good.
And as soon as I get it to Joe, I'm supposed to get it to him today. So it'll get to him tomorrow.
Good.
Later tonight, and I'll post it on the Whac group too.
Well, it would be awfully nice, everybody's appreciated for this. We had a surprise month, none of us knew about, on the first Saturday of the month, and I just happened to be there, so it was recommended.
It's still every
It's very, everybody appreciates greatly, especially the staff and the leaders there, when we come up and do this, they really like it. In other words, if you wanna come, you're most appreciated.
You know, this guy really likes public outreach, I wanna hit him up hard.
Yeah,
Well, we
I
need-
think about it.
Andrew, I heard
Everybody's
last
still
night
off the
that
mountain.
Josh Wallawender is not
Yeah.
joining Keck.
Where do you go?
Josh Wallawinder
I'll
is
tell you later.
indeed joining Keck's staff.
News,
Yeah, he is.
news fly,
He is.
yeah.
He will become a support astronomer along
Yes.
with, well, we've had a couple new support astronomers
Yes.
lately, so.
Josh is.
Yes.
When?
Josh is gonna work for
Starts
Keck.
in March, I believe. He arranged for like a month break between the two jobs, so.
Oh,
He wants to go
fabulous.
play a little bit, but he's also looking for a home now in either Waikoloa or Waimea.
Yeah.
Uh,
Yeah, we need to suggest one.
would he be
because
interested
it really
in
helps
renting
to
a
be
room
very
in the
close to the
meantime?
office for a support astronomer.
Huh?
We have one.
Yeah.
Yeah.
If he's interested, there's one available.
His mom lives in Waimea now too, so,
Oh, okay. That kind of brings him over to the side of the island more than one way.
so yeah, I'm very excited to finally have Josh over here with us. That's gonna be great.
Unfortunately, there's no point in my hitting the new essay up again. Well, like I hit Carlos up. He's the new essay. You need to come do a talk. Doesn't work with Josh. He just spoke with us. How long ago? 6 months ago.
Well, he's always happy.
Yeah.
He's a good guy.
So hopefully Josh will become a regular attendee at these meetings.
Well, Josh, was real huge help. There was a period of time where there was an attempt, which somewhat worked, to get people that were involved with the biz also into, taking astronomical pictures. And Josh used to teach these, and, there were some tremendous pictures taken. And he's very, very good at this.
Yeah.
As is this man over here. And this man
Fantastic.
over here.
Okay, so if
I still
that-
wanna know if you took everybody off the mountain at 10 o'clock and he's not.
No.
All right, the rules is this. Here's the rules. You can stay up the mountain as long as you want. The public, now wait a minute, I'm gonna tell you. The public visitor night nice bathrooms, shut at 10. They do have porta potties. You can now stay up there all night. After a half hour after sunset, they do not want people going beyond the viz to the summit.
Makes sense.
And I am very happy that this is happening.
And they still frown on ramming state cars with your own cars.
Yeah.
That's definitely considered a no-no.
Yes, that happened. Okay.
So that's the deal, and they would be very excited to see us come up and do the new moon thing again. It was great. The guy with the 20-inch scope and some others was up there. It was really nice.
Speaking of 20-inch scopes, we are headed down Saturday morning to Halualoa to pick up an 8 and a 20 that are being donated to CAC.
Oh, excellent.
Yeah, it'd be interesting. I don't know, for the 8's useful. I'm not so sure about the 20s.
What kind of 20?
I don't know. I'm not the one arranging the donation. Mark Cassis is, another one of our supporters from us. So I've just volunteered to go help pack it.
Yeah. Well, that's.
Since I'm the only one that he knows who has experience with such instruments. So.
Well, that sounds great.
Okay, I think we have finished all of the chit chat and arranging that we need to do as a club, at which point it's time to turn the microphone and projector over to our speaker.
Thank you.
So Carlos, you've been with us how long now?
3 months.
3 months. So
Yeah.
we would have had him speaking here earlier. I'd hit him up pretty much the day he showed up.
Yes. It was too much for me.
But
Too many
unfortunately, the
new
last
things.
couple nights of our club meetings corresponded to his being on duty over in remote ops, so we could
That
not.
time.
There's a power cord right here. Yes.
Carlos, where did you come from?
Spain.
Ooh, excellent.
I used to work with Bruno Femenia, which I think you know.
Well,
You know, see.
remember Bruno came to us and gave us the whole talk on the Canary Islands and gave us a
Yes.
good rundown on all the instruments there and the various facilities. Yes.
Well, I'm going to talk about one of those instruments, specifically about Canary Camp. So yeah, but last 9.5 years I was working as a support astronomer for the GTC, from the Grand Telescope
You
of
know
Canarias.
that recently there was a major motion picture shot over there. Ron Howard called In the Heart of the Sea. They use those islands.
I didn't know that.
Yeah, well,
Okay. So how do I connect this? Because I don't have.
You don't have the
no.
VGA adapter.
No, it's not a
In
VGA.
this conference room, do we have an airport here? I don't know.
Well, I need to have some. So
I thought you.
I have a DVI
Oh.
and DVI to HDMI. None of those is gonna work.
We
or-
had No, we may just.
I
We
thought-
may just have the VGA here in this conference room. Our other conference rooms are actually a little bit better equipped. We've
Ah.
got airports and VGA or.
I was assuming that HDMI at least.
No, not in this
No,
conference room. We have
no.
VGA.
You know, is this new Mac that
You always put in a thumb drive and put it in a laptop.
Yeah.
would it be compatible? Is a PowerPoint for Mac? Should work, I guess.
HDMI, but I
Depends
don't
what he's got on
see
his,
a cable around anywhere.
I'm sure he does.
Well,
So-
I can put it. I can put it in memory stick maybe and try from there. I mean,
Oh, yeah,
it's a-
yeah, we'll
it's a-
just
it is
shove
a
it in
po-
here.
It is a PowerPoint for Mac, but it should
It should load
it
fine.
should be compatible. Hopefully.
Yep.
Transfer pretty much.
Yeah, we have translated the other conference rooms over to big flat screens, and they have HDMI and Apple airports and everything on them. But this conference room apparently remains a little bit behind the time. There's an HDMI port on the projector, but there's no. I can't find a cable back. There isn't a cable lying around.
Okay. Well, we'll try this way.
Okay.
See if it
Yeah,
works.
just throw it on a memory stick and we'll get it ported across.
Yes. Hopefully it will work.
We have the technology.
One way or another, we will make this work.
Yes, definitely. So let me see.
we were down for 5. No, really, it was amazing.
How was it Saturday night at the Viz?
It was quite good. It was mild. There was no wind. It was dark. It was clear.
Okay.
And the temperature did get down to freezing again, but it was.
Yeah, because I had at Cahoe at 5,800 feet altitude, just on the old Saddle Road, I had 41 degrees.
Yeah.
But fortunately, no wind to speak of.
No, it dropped below freezing, or at freezing, but that was at the end. It was probably about 34, 35, and
41 when I rolled out, but that's close to midnight.
56 is the house in the village.
Oh, what?
56.
Pretty cool, nice.
Yeah.
Pretty nice.
Any snow on the mountain?
No, just the dusting ones.
Yeah, I was up there today, nothing. Yeah, you can tell when I'm in a,
Just like that.
jeans and t-shirt and
Just like that, yeah.
heavy boots.
Andrew, this year, any tours up the mountain? This year?
I need to do Keck again, I think. Once we're out of winter, springtime, April, May sort of time frame. So let's see, we did last year we did the radio telescopes and
Yeah.
Subaru. So, and we haven't done Keck in a long time.
No,
It's
we
actually the
haven't.
easiest one for me to arrange. So,
That would be very nice.
That would be very nice. I would.
you've all been there.
Yeah, but we can do it again.
Andrew, speaking of radio telescopes, the big news item is the Event Horizon Telescope is supposed to show us
Yeah.
black holes this year. Right?
This year?
Actually,
This year they claim.
the big news that's percolating around in certain circles is LIGO has detected gravitational
Ah, yeah, they
waves.
claim.
Oh
What?
yes,
What?
I heard
It's
that
just a
today.
rumor right now, but
Larry
it has
Krause
not
put
been
that out.
confirmed. So,
But
Wow.
Larry Krause put that out, that he tweeted or something like that.
Yeah.
Larry
I
Krause.
think I saw that.
Yeah, he's a fairly reputable guy, should be.
who knows?
Well, they
Yeah,
tend,
Mine
yeah.
is ready.
So,
They tend to
so
be a
our
little bit,
telescope up there should show us the black
no,
hole sometime this
they
year.
tend to release this news a little bit before they are completely sure about it. So a
Well,
little
that's
bit
just
optimistic.
that's why it's a non-confirmed rumor at this point. There's been no official announcement.
Yes.
Yeah, right.
So that probably is a leak or something that someone
And you guys
heard.
love the burp and the whirlpool with the companion. That was fun.
Galaxy with no matters.
Okay.
Well, that it's several supernovas and everything else.
Yeah.
And it's so photogenic and it's so
Okay, this should be.
Got it. Copy it across. Make sure.
Yes, let me go back in here. How do I eject this? Okay, I did it, alright.
Okay.
So let
Okay.
me, I just copied everything just in case.
Okay.
So I get where I have the figures.
Okay.
So it's a diagram.
Okay, there it is. Just loaded. Removable disk. That's probably it.
And that's it. Well, I copied the whole directory.
Okay, well.
I think we can run it from here.
There
Yeah.
you go.
Good.
Okay.
Woohoo.
Oops. And now we need the projector.
Yes.
So we need to
Replug
plug
in there.
this in back here. That's it.
Hey, looks like we might actually have a talk. Okay. Let's get this full screen. Oh,
F5, isn't it?
I
Is it F5?
never remember.
Yeah, it is
There we
a-
go. I got it.
Okay.
There.
Okey-doke.
Oops. There goes the power.
And there was a laser.
Yes, there's a couple. Actually, this'll you can go forward and back on the slides.
okay, good.
And it's got a laser in it as well. Hang on. We.
Technical problems.
There we go. Okay.
Ah.
The computer might have just gone to sleep when we
Okay,
unplugged
nice.
it there for a moment. Okay.
Mhm.
There we go.
Okay, so well, thanks everyone for coming and thanks for inviting me to talk about a little bit of the work that I was doing, as I said, for the last 9.5 years until I moved here to Hawaii. So I'm gonna talk about mid-infrared astronomy, which is a region of the atmosphere of the mid-infrared instruments, there are, these are basically the mid-infrared instruments. When I created this slide, these were the mid-infrared instruments that were available for large telescopes on the ground. So this is Canarican at the GTC, and these are T-Rex and Michel and Gemini South, Gemini North. Comics, which is an instrument for Subaru, and then Visir at the BLT. These two have been already decommissioned, and Comics is still being used, and Visir is going through a process of refurbishing with a new detector, and is not really back in science yet. This gives you an idea of the type of field of use that these instruments have in arc seconds. So they are relatively small field of use. And these are the different capabilities that the different instruments have. And what I quote here is the sensitivity as a measure of a 5 sigma detection, a signal to noise ratio of 5 in 30 minutes integration. And I use here millijansky, but to get an idea of the equivalent in magnitude at 10 microns, 1 millijansky, what would be 1 millijansky is of the order of 10 magnitudes. 10 magnitudes, but at 10 microns, okay, which is a completely, as I say, it's a completely region of the electromagnetic spectrum to what we are used to. So 10 magnitude is really faint for a ground-based large telescope with a mid-infrared instrument. This is a comparison of the mid-infrared astronomy from the ground. I just use Canarican as an example with what space telescopes can do in the mid-infrared. So again, we are talking about this region of the electromagnetic spectrum that goes from about 8 microns to 25 microns. And as you see here in GTC, these values that we quoted about the sensitivity in millijansky, this is for a ground-based mid-infrared instrument, and this is what the space telescopes can do. So if you look at it, when you look in the mid-infrared through space telescope, the sensitivity kind of gets better by a factor of, you are more sensitive by a factor of 1,000. If you are talking about the James Webb Space Telescope, the sensitivity can go up to 10,000 better than from the ground, even with a smaller size telescopes. This is the diameter of the telescope. The telescope is 10.4 meter telescope. These are 85 centimeter telescopes, 40 centimeter telescopes, and the James Webb that is going to be a 6 meter telescope. So basically, when you compare infrared astronomy from space with infrared astronomy from the ground, there is no competition. The only way in which it is possible to compete is in terms of spatial resolution. So this is the size of your point spread function. What is the resolution of your instrument in terms of arc seconds? And for the GTC, which is limited by the diffraction of the telescope, is 0.25 arc seconds at 10 microns, and it says here millimeters, but it should say microns, and 0.5 arc seconds at 20 microns. The other space telescopes that are more sensitive than Canarican, they have less spatial or worse spatial resolution just because they have a smaller diameter for their telescope. So the diffraction limit is worse, basically. Okay. When we go to the James Webb Space Telescope, it's a 6 meter diameter mirror, then the diffraction limit is also very competitive, even with ground-based 10-meter telescopes. Okay? So basically, the idea when you build a mid-infrared instrument for a large telescope, on the ground, what you want is being able to do this compared to space observations. This column here, these are active galactic nuclei of several galaxies, and these are actually images taken with the Spitzer, and these are the images of the same nuclei, but taken with, in this case, taken with T-Rex, with the mid-infrared instrument that used to be at work in the Gemini South telescope, which is now decommissioned. If you look at it, the level of detail that competitive when you are doing studies that exploit the whole mirror of the size of the mirror of the telescope. Okay, so these are diffraction limited images for an 8-meter telescope. So what we want to do when we build a mid-infrared instrument for a large telescope on the ground is, I say here, high sensitivity, but high sensitivity on the ground is as best as it can get with this fraction of a millijansky that we were talking about, but high sensitivity from the ground is still really, really bad if you compare it with the sensitivity that the space instrument has. Okay? But what you really want to do is to exploit the diffraction limit of the 10-meter clusters. So you really need the whole 10-meter mirror to work as one, and then being able to get the diffraction limit of that mirror. If anything that I say is, I'm just explaining things. If someone doesn't understand what I am saying, or just let me know and I'll try to explain myself better, okay? So what are the challenges of building this? Because the thing is that there used to be many instruments that in the mid-infrared on large telescopes, but all of them are slowly being decommissioned. And the reason why this happens is because it is really tough to do mid-infrared astronomy from the ground. And now we are going to understand why. Okay. So this is the region of the sky. This is basically the sky transmission in the region I was talking about. So this is basically a sky transmission, and this is, we are starting from like 7 microns to 25 microns. The two bands that are observable from the ground in the mid-infrared is this band here, which is the 10 micron window, the M band. This is what is called the M band, and then the 20 micron window. Okay? So as you can see, well, here there are actually 3 colors, and these 3 colors represent a quantity that is fundamental, critical when you are observing in the mid-infrared. That is the amount of water vapor that is on the atmosphere. And I'm not talking about relative humidity. I am talking about how much water vapor, the one that we don't see, not the one that is in clouds, but the one that is in the atmosphere and we don't see because it's in gas state, between your observatory and space. Okay, so that's measured with a parameter that is called precipitable water vapor, which basically means how many millimeters of water you would have if you take all that water that is in the column of atmosphere above your observatory and you just condense. Okay, so if you see here, red means in this case low amount of water vapor in the atmosphere, and green means a lot of water vapor in the atmosphere. So if you look at it, there are these 2 bands, the 10 and the 20 micron bands. The 10 micron is more or less reasonable. Okay, there is a quite relatively good transmission, and if you change, sorry,
It doesn't change much.
and it doesn't change. And in fact, the 10 micron window is relatively stable against changes in water vapor. Okay, so it's you can do a lot of stuff even if there are wide changes in water vapor. The one that kills you is the 20 micron. The 20 micron window really kills you because if you look at all these bands that are here, they are all water vapor bands. Okay, then you have the CO2 that is separating both windows, and then there is this ozone feature here at 9.7 microns. So still in 10 microns you can do things. In 20 microns it is really, really tough. Even from a place like Mauna Kea, it is really, really tough. Because in Mauna Kea is a very good place to observe in the mid-infrared because the column of water vapor that you have is not so high. I mean, you are already at 4,200 meters. But for instance, from La Palma, we tried to do observations at 20 microns, and it was almost impossible. It was basically the atmosphere was opaque. La Palma observatory is at the same height as the Hualalai volcano here. It's 2,400 meters. So, okay.
This window is bigger than that one.
Oh yeah.
Why are the pictures so different? There's only a factor of 2 between them.
What do you mean?
I mean, there's no ozone. Where's the ozone thing over here?
Oh, there is no ozone in this area here. You no, there is no ozone on the 10 micron window, on the 20 micron window. This is all water vapor absorption.
Oh.
All water vapor. Okay, ozone is only here, and these little ones here, they are all water vapor. But where the water vapor absorptions get really, really important is in the 20 micron window. So one of the bad things about the atmosphere is that everything that it is absorbed by the atmosphere, then it is re-emitted. So when you look at the sky emissivity, then you have lots of this. You have the ozone in emission, all these little water lines in emission, and then there are lots of water lines in emission here that they are saturated in this block. So you only have the disadvantage that the wavelengths you want to observe they are absorbed, but then the sky re-emits them, which makes the background of your observations very high, and that's critical. That's what is gonna drive the way it is observed in the medium infrared.
Why is this tipped over from the previous?
Well, because this is in emission. These are emissions. So it's like the water molecules, the ozone molecules, the CO2 molecules, they absorb their radiation in the mid-infrared, but then they re-emit them, okay, in all directions. Of course, you are losing the information from your science target. Okay? The atmosphere is just absorbing them and then re-emitting them. Okay, and that makes the background is really, really, really high. Okay, so 10 microns is a wavelength at which it happens that everything that is at room temperature emits, and that's a problem. So the telescope itself emits. This is actually an image of the GTC pupil taken with the mid-infrared camera canary cam, and then you can see here the spikes from the. These are the these spikes that you see here. They are the support for the secondary mirror. Okay, but you see them instead of a shape, as you would see it in an optical telescope, you see them in emission. They are emitting because they are pieces of metal that they are warm and they emit in the infrared. So that's background in your images. Then, if you see here the little gaps between the segments, these are the segments. As I said, this is the UDC. They are bright. If you were looking at this image in the visible, they would be dark. But here they are bright because there are electronics and there is metal behind the segments, and in the gaps you see that metal emitting. That's another source of background for your images. And then you can even see which mirrors are dirtier and which are cleaner. The ones that are cleaner, they are darker, but the ones that are dirtier, like these ones here, the dust in the mirrors also emits in the infrared. So everything emits. You have sources of emissions everywhere, and that's really, really a problem. That's a challenge.
How much
And
of that
yes.
can you mask any of that off in your instrument, like the spiders?
You can mask this one, but the problem is that if you mask this, you are also. It's very difficult to make a mask in the instrument that matches this thickness. So we have a mask that has the shape of a spider, but then you are losing as well photons from your source, because the way you can, the pupil of the instrument is very small, so when you build it, it's kind of at least this wide. Okay, so we did test with both. That would be good for coronography. For coronography is an advantage, but for normal imaging, because it reduces the diffraction pattern caused by these spiders. But we did test using the mask, and you lose photons from your target as well. So you live with it, and then you use the observing technique which is the chopping and the nodding. I'm going to explain it now to try to cope with that.
calibration point.
Yes, you will see how it works. In fact, the good thing about the positive thing about mid-infrared astronomy is that you don't need flats, you don't need bias, you don't need anything like that, because it is self-calibrated. We'll see how it works. So as I said, everything emits, and of course, humans also emit. So this is actually an image taken during the commissioning of Galactic, in which you can see astronomers and engineers. The telescope was pointing The
Yeah,
telescope was pointing
that's right.
horizontally, and there is a catwalk. And we took images with canary gun, and you have the engineers and the astronomers
You
doing
guys were
the-
having too much fun.
Yeah.
having a lot of fun, and you see how bright they emit. I mean, they are really bright. We
Yeah,
are
but the
really
rest of the
bright
background is disappearing.
in the infrared. Okay, so that's these are humans. These are humans, but of course, everything that is around in the dome, electronics, etc., that is warm, also emits. Okay, so those are also, and now the pupil, we were actually rotating the rotator where the instrument is mounted, so now the catwalk is horizontal. Because before the catwalk was like on a
Is there
slab.
any way it's only men and women in the?
Oh no, there is no way. Well, maybe there is a way of telling between engineers and astronomers. Probably the engineers have like more blood in their head, they think more than the astronomers. Okay, so when you put everything in perspective, this is actually the emissivity of the telescope, and this is the sky emissivity that I was showing before. So the emissivity of the telescope is not really relevant when you are in the 20 microns band, but when you are in the 10 microns band, your telescope, the emissivity from your telescope is higher than the emissivity from the sky. Okay, so these are things that you need to take into account when you do the observations. So one way of making, and this is the first thing that makes the telescope, makes a design for a mid-infrared telescope, mid-infrared optimized telescope difficult. One of the things that you need to do, the pupil of the telescope, in the case of the GPC, is on the secondary mirror. So the secondary mirror, this actually, the outer shape here is the primary mirror projected on the secondary mirror, and the dot line here is actually the size of the secondary mirror. So the secondary mirror is slightly undersized to make sure that you don't have any background radiation from outside, from all the metal that is supporting the external parts of the primary mirror. So that's one of the things that you need to do, is to make the pupil underside, and then you have to do a secondary mirror that is not circular in shape. That's got the shape of the telescope pupil, because you want to optimize the amount of light that you get from your scientific target. And this actually is one of the most expensive piece of equipment in the whole UPC. Like single piece of equipment is the secondary mirror. It had to be done 3 times. It broke twice, and at the 3rd time, we got it. So it is a really delicate piece of equipment, and it's just because it's got to be mid-infrared optimized.
You get a chance to go up and look at the 25 secondary.
It's the one that it was used for LWS, wasn't it?
Yeah.
There was a mid-infrared instrument.
It's got the pupil shape.
Yes, because it is optimized for the mid-infrared. So basically, the other thing that so this is actually the telescope secondary mirror. You have here a nice view of it. And then the other thing that you need to have is this deployable baffles. The idea is when you are observing in the visible, you know this quite well. You don't want any stray light coming into your field. So you need these baffles to be deployed. But when you, and even the one that is, there is one here on the back that is covering the central hole of the secondary mirror. But that's if you are observing in the visible. But if you are observing in the mid-infrared, you don't want even more metal around emitting. So you just have to take them away from the optical path. So basically they are deployed or removed depending on whether you are observing in the visible or you are observing in the infrared.
Can't quite make it out there. Are they actuated pedals?
Yes. So they are. So these ones actually move. So if I am the secondary mirror looking to the primary mirror, they just fold in when you are observing in the infrared. And the one on the back, they are 4 petals. They open like this, and then you have just the background sky, which is lower than the background from the metal that is at the telescope. Well, but they are quite well behaved. So the ones at UPC, they are quite well behaved.
Are the ones in Kecker rollers?
Okay.
The motors and the gearboxes are old.
Okay, so the other thing that you need to do, and this is quite a funny thing, if you take an image, now say that you want to observe a galaxy. In this case, it's a standard star, which is very, very bright. It's a really bright object in the infrared. Okay, but when you point your telescope at this region of the sky where your star or your galaxy is, and you take an image, you see this really background emission. You don't see anything. You just see background photons. The sky, the telescope, everything is emitting. Okay, so what do? What you do is this thing called chopping, which the secondary mirror must be able to do, which is just an oscillation of the secondary mirror, and then you take an image with the secondary mirror pointing, aligned with the primary mirror, and then just tilt the secondary mirror a little bit, take another image, and then just subtract one of the other one. And when you do this, you get, so this is what is called on source. The secondary mirror is aligned with the primary mirror, and then you tilt the secondary mirror. This is called, this is our frame off source. And when you subtract it, you get a positive image and a negative image of your target, depending on how much you tilt your secondary mirror. If you tilt it a lot, your negative image will go off the field of view. Okay. Do you see how it goes? So basically, and this is got to be done continuously during the observation. Otherwise, you wouldn't be able to see anything on your images. Okay? So typically, for you to have an idea for a scientific target, as I said, this is a relatively bright target, but for a scientific target, any typical scientific target that you want to observe, for every 10,000 photons that get into your detector, one of those photons is from your scientific target, and the rest is just background emission. Of course, this doesn't happen in the visible. Even in the days that you have like a full moon, you don't have this kind of background emission, but you have it in the mid-infrared. Okay? So the problem now is not only sufficient if you just, when you do this chopping, okay, this chopping, really you are not looking at the same region of the sky when you are pointing at your target as when you have your telescope tilted, your secondary mirror tilted, and you are not seeing even the same background from your telescope, because now the secondary mirror is tilted, so the amount of background that you are seeing is slightly, the region of the telescope background that you are looking at is slightly different. So if you do that, you have reminder background, which is called radiative offset, and to correct that reminder background, you not only have to chop, but you also have to knot the telescope between the position of the sky and the position of your target. Okay. So basically what happens here, and the speed at which you do the knotting, it is relevant. Because if you think about it, when you have a telescope which has an azimuth mounting, like this one, and the instrument is mounted on an azimuth focus, when you are tracking the sky, the pupil is rotating, isn't it?
Right.
The pupil is rotating. So then you have this remaining background that you cannot correct just only by doing chopping, because the pupil is rotating. So what you see, if you do this nodding, here, this is just an image of the sky, okay? And this is, so this is an image of the sky, and this is, of course, the speed at which your field is going to rotate, your pupil is going to rotate, is going to depend on the elevation. So when you do the nodding, if you do a nodding, one of these nods every 60 seconds, every minute, you get this kind of hexagonal structure. This is actually the power spectrum of it, so you can see this hexagonal structure better, but you have this hexagonal structure in the background, which is due to the fact that the pupil has rotated a lot in these 60 seconds. If you nod faster, at 45 seconds, then you don't see that structure. So then you know that this is your nod time. That is the time that you need between, so you are doing chopping continuously, and then you nod the telescope, and you have to do it at a certain speed to avoid this background structure. Okay,
So how fast is the chopping taking place on here again?
so the chopping is taking place at 2 Hertz. That's my next slide. Well, basically this is a sketch. This is not, but this is for you to visualize a little bit what the chopping and nodding is. Okay, so you are pointing at your object. This is the secondary. This is the primary. This is chopping. So the secondary is oscillating between this and this. Tick, 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 tick. And then from time to time you do a nod, which basically means that you point the telescope at the region of the sky, which was obtained when you were doing the nodding, okay? But the secondary mirror is still chopping while you do that, okay? And at some point, when you do the arithmetics with the images, you get an image of your target. Basically, basically you have to visualize the secondary mirror chopping, and then the telescope nodding while you are chopping. But the frequencies, and this is this slide here, it responds your answer. This is answers your question. The secondary mirror chops at 2 hertz, while the nodes occur every 45 seconds. Okay, and that's another big design driver for the secondary mirror. It has to be very light. In fact, the secondary mirror of DTC. So the primary mirror is the same as in Keck. It's made, so the substrate is made of cerulean, and the weight of each of the segments for the primary mirror is about 500 kilos, half a ton, which I think is very similar to Keck telescope primary mirror segment.
We usually figure a ton complete with support structure.
Well, with the support structure, but what is the segment itself? It weighs about
Yeah, in that sort of range.
half a ton or something like. Well, for the GTC, the primary mirror segments are half a ton, but the secondary mirror weighs only 40 kilos. And this is because it's made, the substrate, instead of being cerulean, is beryllium. And the beryllium is very difficult to work on, and that's why it broke 3 times when they were trying to build this thing, especially with this weird, with the pupil, the telescope pupil shape. So, and why is it going to be so light? Because if you had the secondary mirror made of cerulean, probably it would weigh like 200 kilos. Sorry, I know I'm saying it correct, 200 kilos, or maybe 300 kilos. It's 1.2 meters from edge to edge, the secondary mirror, okay? So you wouldn't be able to do this chopping at 2 hertz. The inertial mass would be too high. So that's why it's made of cerulean, of beryllium. Okay? So the other thing that you want to do is to reach the diffraction limit of the telescope. Here is, my image is gone. Oh, this must be one of the things that happens when you convert between. Yes. Okay, so there was a very nice simulation that I had done here of the diffraction pattern, the ID function, for a 4-meter telescope and for an 8-meter telescope. And of course, the diffraction pattern for the 4-meter telescope is bigger. Okay. Basically, that's what you would get from your telescope if you didn't have any aberrations, any optical aberrations. Really a shame. Because I had a very nice image here of an hexagonal pupil, and then the diffraction figure for an hexagonal pupil at 2.5 miles. Okay, so you can imagine that gets smaller.
Imagine a blurry hexagon.
Yes, it's very nice PSA, very nice point spread function. Okay. Oh, this is too bad. I don't like this anymore.
Not completely compatible.
Yes, it is really a shame. Well,
all of us have seen what the scene
yes.
does in our
You
own
know what it is. So
telescope. Imagine
basically,
the blurry DNC dot.
yeah. Basically, I have here a speckle pattern, okay,
Yeah.
and then I have here the integrated image of the speckle pattern, which is you're seeing this, and then I have here what happens when you just align that speckle pattern, and what was here a blur with a very big full width maximum here happened to be a double star, okay, which is the typical example. And as I say here, the atmosphere gets in the way again. Okay, this time it's just
many of us
blur.
have practical experience here, so I think you're
Yes,
okay.
yeah. Oh my God, this one was important.
No.
Oh, this one I would. Well, okay, so you have to imagine a plot here in which basically you see the diffraction limit of the telescope increasing with wavelength, because that's the important point of all this. Okay, so as you go to longer wavelengths, as you go from the visible to the infrared, the ID function grows, but the scene decreases as you go to longer wavelengths. And there is a crossing point for a 10-meter telescope, which is at about 10 microns, where the diffraction limit of the telescope is bigger than the scene limit. So you can actually we know that with Keck telescope you can almost get the diffraction limit of the telescope by using adapted optics. Okay, but that's when you do that between 1 and 2.5 microns in the near infrared. When you go to 10 microns, you can get the diffraction limit of the telescope without the need of adapted optics. Okay, something that comes natural because you are at the region of this electromagnetic spectrum where the atmospheric distortion that causes the scene is smaller than the actual diffraction limit of the telescope, which grows with wavelength. Okay, so that was very nicely shown in a plot. The plot is gone.
So, wait, no, just a
Yes.
question. So on this plot, on your horizontal axis,
Is there a whiteboard?
It's wavelength.
it's wavelength on the
Oh yeah,
horizontal.
sure, yeah, of course, yeah.
Horizontal
Wavelength against full width Hall maximum, okay? Or yeah, seeing this full
Now I
width Hall
can
maximum.
imagine the plot.
Okay, so but more or less you have an idea of what I am talking about, okay? Oh, this is so bad. There were plenty of nice pictures here. I really hate
But you
this.
can show it to us in the.
Yes, I'm gonna
On
do.
the Mac and just
I'm
turn
gonna
around.
do. I'm gonna do this. I'm sorry because they are so
Yeah,
nice
just bring it up
pictures.
on the map.
Yeah, yeah. It's
So
show it to
it is a shame that I don't see it.
Oh.
Oh, this cannot be possible. This cannot be happening. We should have thought about this, Andrew.
I thought you used this conference room before, but I guess not.
No, not with the Mac.
Yeah.
Don't try to sit down.
Oh, okay. So let's do a combination between. So let's see. Okay.
Ooh, lovely picture.
Well, even
Yeah.
even in the near infrared, the nodding is a standard technique that we do with the Keck telescope. We don't do the chopping because the only chopping secondary Keck has, which are 25 secondary, is currently decommissioned. It's sitting up on the deck, just in storage essentially. We don't have an instrument that works with it. We don't have a
Okay.
for an instrument.
So this was my nice. Oops. This was my nice simulation. Sorry, I have to show this because I took the time to do them. So this was my nice simulation of. Sorry, this was my nice simulation of a circular pupil, PSF, diffraction limited with no aberrations, of a 4-meter telescope and an 8-meter telescope. And this is actually a scale. I mean, these are the images are at the same scale, and this is for 2.5 microns wavelength. Okay. And then when you go to the hexagonal pupil, the GTC, this is actually the GTC pupil. It's a simulation of the GTC pupil. You see that the full width Hall maximum is smaller, okay? And then you have all this hexagonal figure, which is related to the hexagons that are forming part of the primary mirror, okay? And now, this is the scene picture that I wanted to show. I know that you know the scene, but you know a lot about the scene, more than I, definitely. But this is basically what you have when you take very short exposures,
Yep, you get
milliseconds
that.
exposure. So you get this blurry thing dancing around,
Yeah.
and this is your scene spot. And then when you align the speckles that you see in here, you get what was a binary star in this case. Okay. And this is the plot. Now you don't have to imagine anymore. Okay, so this is the scene going down as a function of wavelength, and this is actually the diffraction limit of the telescope going up as a function of wavelength. And the one for a 10-meter telescope is the middle line, and they cross basically at a little bit higher, longer wavelength than.
No point in
10.
using an AO system anything longer than 10 microns.
Unless you have a 30-meter telescope.
Well, okay.
Of course,
Okay.
we do want that.
Yes, or a 40-meter telescope. So the TNT and the ELT, they have planned with infrared instruments, but they need to work with with an AO system, which is challenging. I mean, to have an AO system that can correct in the so you've got to do the correction in the visible, or maybe in the near infrared.
The AO system means you have a lot more optics in there, and they all emit. So now you have to have a cold AO system.
It is really tough. So.
Because the other way to stop your optics from emitting is to put those optics in a vacuum, suck the air out, and chill everything down. And now your optics won't emit at the wavelengths you're worried about.
You are worried about. And then you have the challenge on at which wavelength are you going to be able to do because normally the AO systems, they have the reference star for the adaptive optics is in the visible.
Right.
Unless you have an infrared wavefront sensor, but even if you have an infrared wavefront sensor that has enough and signal to noise ratio, still you have the problems that you are going to be correcting probably at one point in the H band at 1.6 microns, but you are observing at 10 microns, 20 microns. So it is really challenging. They are planned, but we'll see if they manage to really build one of these for the 10, 8, the 30, 40 meter telescopes. Okay, so basically, those nice PSFs were without optical aberrations. When you add the optical aberrations, and in a segmented mirror you have two types of optical aberrations. Let's see if these ones work. And then I can show it. So let me go. No, okay. So you have two types of optical aberrations that you can measure. This is actually a map of the aberrations of a GTC image, a real map. You have two types of optical aberrations, which are the aberrations of each of the segments individually, and then actually the aberrations of the whole mirror. But then you also have the problem that the 36 segments, they've got to be stacked, like to form one single image. Okay, and that stacking has its error as well. So here there is an example of a stacking that has an RMS of 0.05 arseconds. And if you think about it, at 10 microns, the diffraction limit, what you want to reach is 0.17 arseconds. So only the fact that the 36 segments are not exactly aligned one to each other, because there is much that you can do to align them, only that is already an important fraction of the diffraction limit that you want to reach for your 10-meter telescope. Okay, so that's another type of challenge that you have. Okay. So let's see if this one, I hope that this one works. Oh, it doesn't really work. I think they are PNGs.
Yeah, for some reason.
And PNGs, they have transparency or something like that, and probably they don't talk correctly.
You've got to use JIT and JPEG if you expect global.
Yeah, but I wasn't expected to do it in this one. So.
Yeah, I know, I like PNGs for some things.
Okay, so basically this is a very nice image which shows you the diffraction. These are actual real images of a standard star with GTC. And you have here at the image at 8.7 microns. This is at 11.6 microns, and this is at 20.5 microns and 17.65 microns. And you can clearly see the diffraction rings, although the images are not exactly diffraction limited. I have an example here. The diffraction limit, for instance, at 8.7 microns is 0.18 arseconds, and what we achieve is 0.25 arseconds, okay, due to all these aberrations that you can correct to certain extent. As you go to longer wavelengths, it is easier to reach the diffraction limit as well. This one, in fact, you could see this one, it is a little bit affected by scene. Okay, the number of speckles that you have in the infrared are less because you are in the infrared, but still at 8 microns you are more affected by scene, while when you go to the 20 micron wavelength range, the scene almost doesn't affect you. So then you get a better image quality in terms of being closer to the diffraction limit when you go to 20 microns wavelength. But basically this is what you want to achieve. You want to achieve diffraction limited images with your instrument in a 10-meter telescope. Okay, so the instrument itself, so that was a little bit about the difficulties. Okay, so you need to have the chopping and knotting. You have the problem that you have a very high background, and then you have all the optical aberrations that are affecting to your system, and you kind of, since you want to be diffraction limited, they are quite relevant. While when you are limited by seeing, most of those effects are second order effects, and your major problem is the seeing. Okay? Terrible, eh? Okay, I'll carry on in this one. Terrible, I mean the fact that I cannot see, I cannot show. Okay, so let's do it in here. So basically, this is just to remind, and Bruno talked about this in his talk, definitely, but it's just to remind you where the telescope is. So this is the GTC. This is the Roque de los Muchachos Observatory. As I was saying, it's 2,400 meters above the sea level. And this is in the tiny island of La Palma, which is even smaller. It's slightly smaller than Oahu, which is off the African coast, but it's part of Spain. Okay, so there are several telescopes in there, and the GTC is one of them. The instrument, well, I was just mentioning here, so this is a nice image of the GTC. It's very similar to one that I've seen around of Keck, where you have two GTC staff, like little people here. There are these two people here, and you can see the whole size of the telescope, which is very nice. So it's an optical and infrared telescope. It has 36 segments, a primary segmented mirror, and it has the equivalent area of a circular pupil with 10.4 meter diameter. Okay, and bless you. And it has capacity for up to 7 instruments, and there are currently 3 instruments which are in operation, and one of them is the mid-infrared camera, which is basically, these are the specifications. The important thing is that the spectral range is from 8 to 25 microns. Or maybe that one.
I'll follow along on the other one.
Oh, okay. Thank you. Yeah, maybe this one is going to work.
This one
Okay,
will work,
this
yeah.
one works.
So here we can follow along with the two computers
Okay.
side by side.
Thank you, Andrew. That's great. So basically, the most important thing here is 8 to 25 microns, as I was saying before, and the field of view is quite small. You see, it's 25 arc seconds by 19 arc seconds. Okay, so they are instruments that, when you compare with the optical instruments in these large telescopes, they have a very small field of view. It is designed to be diffraction limited. Okay, and then it has, you can do imaging, spectroscopy, spectropolarimetry. You can do imaging, polarimetry, spectropolarimetry, and you can do coronagraphy, which is important when you are doing search for planets and these kind of things. Okay, so this is an image of Canary Camp, the telescope, when it was being, one of the times that was being installed in there, because it had to be serviced several times, and I'll talk about this in a couple of slides. But basically, this gives you an idea of the size of the instrument. That's another thing, that if you compare this type of instrument, which is something like a cubic meter of instrument, with the large DEMOS is one of the optical instruments for Keck. The optical instrument for GTC is called Osiris, which is nothing to do with the Osiris that we have here at Keck, but they are huge instruments. The volume is huge. In this case, they are relatively compact instruments. They are very small, and one of the reasons is because they have to be cooled down. They have to be, the whole optics has to be in a cryostat at very low temperature. Okay. So these are some of the optical components. This is really not much relevant. Okay, you have a different. Basically, you have an entrance window, and then you have filter wheel, aperture wheel. You have to fold the optical path because you want to pack everything in this little hexagon, which is 1 cubic meter. So you have like the whole optics is in the upper, you have a middle part, and then you have the upper deck and the lower deck, and everything is folded around. So you can fit everything in this 1 cubic meter cryostat or viewer, okay? And just for you to have an idea, this is the entrance window. So you have here the entrance window, which is a kind of curious device, because as you can see in here, the temperature inside the cryostat is of the order of 70 Kelvin. It's minus 200 degrees. And the only thing that you have, apart from the whole cryostat, the only thing that you have to separate that from the outside is this window, which can rotate, but it's got to be able to rotate while keeping 10 to the minus 7 millibars inside the cryostat, plus 70 Kelvin. Okay, so there is the way to do this. There is a ferrofluid, yeah, which just keeps everything tight, which is really amazing. So you can rotate even though you have a huge difference in pressure and temperature from the outside.
I think the only ferrofluid feature we have at Keck is actually in the trick camera on the A08.
Makes sense.
Yeah.
Okay. So and that's amazing. When I found out about that, it's really amazing. You know that you can actually rotate things and be completely separated from the outside.
Ferrofluid is essentially an iron particle or a paste of iron particles suspended in oil, and then you put it between a heavy magnetic field, and it keeps it from leaking out everywhere. It stays right where you put it. And you can actually use it for a moving vacuum seal, because the ferrofluid is a fluid, so it's like making a gasket out of fluid. Yeah, it actually is a cute trick.
It is amazing. I found it the first time that I found about this is like wow, because it took me a while to figure out, because I knew that when I started to work with this instrument, I knew that the window could change, and I was like, I mean, you can really rotate the window. How do you do it? I mean, because you typically think of bearings and these kind of things. It's like, how do they do it? And then I found out about this ferrofluidic. It looks to me like science fiction, you know. Really.
You can actually make a ferrofluid by just taking powdered iron and mixing it in oil. And then you can put it in a beaker or something, manipulate it with a magnet.
Giving it shapes.
If you have a pool of this stuff in a tray and you drop a magnet right in the middle, the stuff will actually flow up and over the magnets.
Wow.
Oh, probably you could be able even to trace the magnetic field lines or something like that. Do you do something like that?
Just there's actually just go YouTube search ferrofluid and watch this stuff move. It's like, ooh, is this alive?
Okay.
F-E-R-R-O.
Ferro, yeah, like from iron. So one of the ferro is actually from Latin, yeah, from iron in Latin. So, okay, so one of the other things that is quite impressive is, of course, the detectors. We know that the detectors tend to heat up, and you need to keep the detector very, very cold to be able to do observations in the mid-infrared. There is a cooling system that works with an helium circulation system with a cold head. And that helium system keeps the detector at 7 Kelvin, and you have to control the temperature of the detector to levels of millikelvin, because otherwise, if you have variations on the temperature of the detector, you will have the problem that when you are chopping and you are nodding, the background will not subtract correctly. Okay, so you really need to have that at a very cold temperature and very, very stable temperature. And it's curious, the way it is done is the helium cools it a lot, more than it should, and then you use a heater to keep the temperature constant. So the closed loop for keeping the temperature within millikelvins is just by heating what the helium first cools down. So you cool it to a temperature of about 7 Kelvin, but then the heater keeps it at the nominal operation temperature of the detector is 9.5 Kelvin. And this is really, we are talking about minus 260 centigrades, you know. So it can be done. And this is actually the cold head. This one here is the cold head, which is just a pumping mechanism. It's a cylinder that pumps in and out helium. There is not direct contact between the helium and the detector. It just extracts the heat. This one is more like, this one has a cycle of 1 hertz and it's more like. So when you are at the telescope dome, you just.
When you're in the dome, it's about all you hear all day long. Squeak, squeak.
Okay, so well, here there were some of the mechanism. This is an image of the no, nothing there. Okay, this is an image of the commissioning of the instrument, which was done in 2011, And then one of the first images that while I was working at GTC, this was in 2011, I never thought I was going to be working at Cake, but what happened that when you commission an instrument, the first thing that you want to do is to observe something that someone else has already observed, and that is very, very, very bright, that is very nice, aesthetically speaking, and that has a structure, and you want to see if you can do better than the others.
Yeah, right.
And we did it at that point. Okay, now they are the competition. This is the competition, but this is an image taken of the BNKL. BNKL is one of the brightest. It's actually one of the brightest objects in the mid-infrared. When you look at the sky, this is in Orion. It's a star-forming region that is very close to the trapezium, but you don't see it in the visible. You only see it in the mid-infrared. It glows very brightly in the mid-infrared. And this is an image taken of this object, this star-forming region with a lot of gas there, and the main John stellar object is a massive John stellar object. This object has more than 10 times the mass of the sun, and it's been forming in the cocoon there of dust and gas. So this was observed with the Keck mid-infrared camera, which was the commission. Do you know how long ago it was? A long time ago. Okay, but this image is from 2002, and this image is taken. So this is just one image taken in the at 12.5 microns. Again, this is millimeters, but it should say microns. And this is actually a 3-color image of the same region of the sky, taken at 17.65 microns, 11.3 microns, and 8.99 microns. Okay, and this is a color composition that I created. So if you see, this one was made, the LWS instrument had a smaller field of view, 10 by 10 arc seconds. Canarican has a field of view of 25 by 19 arc seconds. This was a total integration time of 828 seconds, quite bright object, but to do they had to do a mosaic here. So they had to do a dithering pattern to cover the whole area, while this is just one shot in 3 different filters, and the total time is 159 seconds. So it was able to reach the same level of sensitivity with less exposure time and in different wavelengths. Okay, and that's because the main reason is because it's a newer instrument. That's it. And LWS was a mid-infrared instrument, but was already quite old.
That's in the trapezium itself?
No, it is off the trapezium. Okay, it's actually, when you see the images in the visible, it's a dark region. I should have brought it's in the fish head then. It is of the. I should have shown an image in the visible, but I don't remember exactly how off is from the trapezium, but it's in the trapezium area, but off.
It's just north of the trapezium.
North, I think it's northeast.
Yeah.
It's northeast of the trapezium, but I don't have exactly.
Now this object that you're looking at is a forming star, right?
Oh yes. This is, as I say, when you look at this in the
mass of 10 suns.
yes, 10 solar masses.
Yeah.
Minimum. I mean, this is super bright in the infrared, but in the visible you just see a dark spot.
Now it's already turned on, or is it starting?
Well,
They don't
that's
know
a very
yet.
good question. When you are talking about massive massive stars in the process of being formed,
Right.
it's not so clear. So the paradigm of star formation for low mass stars, which you have your
Right.
molecular cloud that is collapsing, and then you have disk around it,
Right,
and
right,
normally you
right.
have the HH objects, which are these very
Right,
nice
right,
bipolar
right.
jets. That's not so clear. I did my thesis, in fact, on massive solar stars, studying massive John stellar objects in high resolution, trying to see if I could find jets, the same type of jets that you find in low mass stars, which are these jets are associated with the magnetic field, in the interaction of the magnetic field between the disk and the forming star, and I couldn't find them.
Yeah,
So it's the formation process is slightly different. So you could have this already on, even when it is within the cocoon, while in the young when you are talking about low mass stars,
Yeah.
typically you clear out
That's
a lot
right.
of dust and gas
Right.
before they are turned on.
Yeah.
Okay,
But
it
this
is-
could be the opposite.
Sorry? Yes.
Yeah,
This
that's
is
very fast.
everything happens much faster when you are talking about massive stars.
Yeah.
Isn't it? I mean, these are almost after being formed a few million years after, and it's a
That's it.
supernova.
Yeah.
So.
That's what's wonderful when you show people the Orion Nebula and you start talking about how young the stars are and what they'll do. It gets to be really
Yeah,
fun.
yeah. I mean, these objects in a million years they won't be there anymore. In
That's
a million
right.
years, you know. And then you have all the brown dwarfs that are around it. That when you go through the whole initial mass function, you have all the low mass stars there that they are being formed. That they are going to be there for billions of years.
Yeah,
So.
yeah.
But it's not clear what is, and this is why it is still being studied. Okay. The problem when you have an isolated massive ion stellar objects is it is relatively easier to understand, especially if you want to see if there are disks or something like that. You can look for disks using polarimetry. Okay, that's a way of doing it. But in this complex region, it's more difficult because there are lots of things that are interacting there. So if you are looking at the magnetic field structure in here, it's very messy because there are lots of contributions in there. So, okay, so this was like a demonstration image that the instrument was working, and I'm just gonna talk. I'm gonna end with talking. Oh well, this is just the last thing about operation difficulties. So basically, the cold head is very difficult to operate. In fact, for the GTC, this is the cylinder for this helium cold head. It has here O-rings that they wear out, and they wear out really quick. We had to replace this cold head almost every 4 months, sometimes every 3 months. So every 3 months was a standout that would require the instrument to be taken out of the Nasdaq focus, and then it had to be repaired, and then you see.
Oh, yeah.
Yeah. So, and then the other problem that we had, you had the helium circulation system, and the helium circulation system could get contaminated. And then the cooling efficiency was not as good as it should be. So the maintenance of these systems is really, really tricky. It's really complicated. And that's one of the reasons I think why this type of instrumentation is being decommissioned from many telescopes, because it is very tough. It's difficult to maintain. Okay, the chopping secondary is another thing that is difficult to maintain. Sometimes you can have failures, although in the case of the GTC it worked quite well. I mean, we only had one incident in which there were problems with the secondary mirror, but in general it worked really really well. And the other thing is that mid-infrared astronomy is something that we have to face. There are not so many astronomers, even in the professional world, that they are interested in mid-infrared astronomy. I mean, if you look at, at the time I was there, we only had 2 instruments in operation, and Canaricam would take only 10% of the observing time. The rest was for the optical instrument. So in the end,
Then you have a chicken or egg problem. That you have no mid-infrared astronomers because there's very little instrumentation and very little data to work on, or you have very few instruments because there's just not much interest in the field.
I think it's the second one. I mean, there are not too many astronomers educated, professional astronomers educated to observe in the mid-infrared. But I think the key of all this is that it's not building an optical instrument is relatively easy nowadays. I mean, it is something, a CCD, in general, you don't have to worry about vacuum and these kind of things. You only worry about the cryostat for the detector, and you just fill it in with liquid nitrogen. It's relatively, I mean, I'm not saying that it's super easy, but it's relatively easy. This is really another level. This is really complicated, and that's why you take this to space. You put something like this. Yeah, you put this in the James Webb Space Telescope that is going to be in the L2 point, and you don't need
your whole telescope structure is at 3 Kelvin.
you don't need
helium.
helium. Yes, you don't need helium, and that's why you get 10,000 times more sensitivity when you go to space. So if you manage to build a big telescope, and I think that's the other reason. You know, everyone is thinking the day James Webb Space Telescope is going to be launched and it starts working, all this useless. because it's gonna get the same spatial.
Well, it's not so much that it's useless, it's that all the work right now lays the groundwork for the science that'll happen.
But then with these instruments, you will always be able to do the brightest targets that you cannot do with the James Webb Space Telescope because they will saturate.
Yeah.
You know, they are so
right.
bright that they will
Yeah.
saturate, and so you will be able only to do the bright targets, and then in terms of sensitivity, it's gonna be able. When we only had the small telescopes on space telescopes, small space telescopes, and I'm talking about half a meter, 80 centimeters, it made sense because then you can compete with spatial resolution, even if you don't have the sensitivity. But as soon as you have the James Webb Space Telescope on the sky, you cannot compete anymore with neither with sensitivity nor with resolution unless you have a 30-meter or 40-meter telescope. So
Oh,
that's
we
it.
get it, I hope it works.
Yeah, well, and it's got to work. That's another thing.
Well, that's a big question with the web too.
Yeah, no. I mean with the web. No. I think you were talking about the web. Weren't
Yeah, I
you?
was talking
Yeah,
about
I
the
was
web.
talking about the web too. So.
Well, if it doesn't work, you got a big problem.
Okay, so a couple of things about science. There is a Canadian science team, and basically the type of things that you can do in the mid-infrared is studying disks around stars, debris disks. They have dust. Everything that has a lot of dust, you can do in the mid-infrared. Okay, you can study substellar objects because they are also bright in the infrared, even if they are weak in the visible, and you can study active galactic nuclei. Okay, so I'm gonna show here an example of an active galactic nuclei. This object is called Macarian 1066. This is an image in the visible, and this is a kind of a dummy model of what is going on in the nucleus of the galaxy. And everything happens where you have, as you know, when you have active galactic nuclei, you have a torus, you have an accretion disk, and you have a supermassive black hole in the center.
Yeah.
And that's when we are talking about supermassive black holes, we are talking about billions of solar masses compared with the galactic or galaxy black hole, which is only 4.5 million solar masses. And there is a lot of emission in the mid-infrared, but everything happens at a very small spatial scale. So what you want to do is you want to study this infrared emission very close to the galactic nucleus. To do that, you need a high spatial resolution because otherwise all this information here gets blurred if you are using a telescope that doesn't have enough spatial resolution. And this is some of the work that has been done. Basically, when you have the supermassive black hole, you also have a star formation around that supermassive black hole. And one of the things that you can do with Canary Can is to study the interplay between this supermassive black hole and the star formation. And one of the questions about this is, since you have this supermassive black hole that is emitting a lot of energy, one of the things that could happen is that that energy that is being emitted by the supermassive black hole could stop the formation of stars, because most of the molecules that are associated with the star formation, they would be destroyed. With this study with Canary Can shown for this galaxy in particular is that the dusty envelope, the dusty torus is so thick that those molecules are actually protected, and you can still have star formation when you are going very close to the supermassive black hole. And we are talking here about distances. We are talking here about the spatial scales of the order of 100 parsec, which is actually pretty good for a galaxy that is 47 megaparsec away. So it's a galaxy that is really, really far away, but with Canary Can you can really peer into the nuclear region. You cannot really see the accretion disk or the torus, but you can get very close to where those structures live and try to find out what is going on in that area. Okay, so that's one of the this one of the articles. This one was one of the first papers published with Canary Can. The other thing that you can do is, in this case, probably everyone is familiar with this star. Oh, it's really so sad. So which one is the star that moves fastest on the sky? Barnard's star. Okay, it's the star that has the highest proper motion on the sky. It's a star that is at only 1.83 parsecs, so a few light years, And one thing that we did with Canary Can was trying to detect if there are companions, planetary mass companions around this star. Okay?
And did you guys find out anything about it?
Okay, so this is the next slide. What we found with Canary Can, in fact, you can go deeper than with any other surveys. A lot of people have studied this star to find out if it has planets. So we could, and these are some of the images taken with Canary Can with the subtraction of the central hole, of the central peak to enhance the contrast. What we found is that in distance between 2 astronomical units and 12 astronomical units from the star, from the Barnard star, if there are planets, they should be less massive than 13 Jupiter masses. So basically we put an upper limit for the possible planets that you can have in that region. Basically it means that
So
they are not
13
super...
Jupiter masses is pretty big. So
It
that's-
is
yeah.
pretty big, but it's in the planetary, still pretty big, yeah. I mean, it's...
So that's a pretty high bar.
Yes, it is a high bar, but it was not clear. Actually, it is a high bar, but if you look, so basically here you have the detectability margins with Canary Can compared with other surveys that have been done before, and this one is the deepest. So this is a very high bar, but it's the lowest of all the high bars that have been able to, at these distances. Remember that when you do exoplanet search, typically you use either the radial velocity method or you use the transit method.
Right.
And those are very good when you are looking for planets very close to the star.
Right.
Okay? But when you
Also
go,
helps if the planetary orbit is
and then
somewhat aligned
plus
with-
all,
Right.
yeah, plus that. Okay? But still, even if you are lucky that the planet is just on the orbit of is aligned with your line of sight, you are sensitive only to planets that are very close. In this case, you are sensitive outside that region. And actually, the region of interest, 2 astronomical units is kind of an interesting region. 10 astronomical units is kind of where the giant planets in our solar system are. So
Right.
you want to find if there are planets in there as well. And you cannot use, for that, you cannot use radial velocity or transits, because even if they are aligned on the line of sight, it's going to take ages. It's going to take 5 years to find one of these. So,
Right.
okay.
The data sets for radial are now longer than that, so yeah.
Yeah, now with Kepler they are getting better, but it's still sensitive more to the inner region and to.
So,
Yes.
in the data reduction, was there any clues that you actually did find some 10 mass stars? Or
No. In fact, we did this in 2 different ways. One was, as you see here, subtracting the PSF and looking for stuff in the background, and the other thing was creating artificial
Right.
planets
Right.
and just putting them at different separations and see if you could detect them. So that was actually what was giving our final detectability limit. You could create a PSF corresponding to a planet which has this contrast with respect to your star, okay, and see how bright this planet has to be for you to be able to detect. Okay, and the eye is very good at detecting these things.
Yeah.
Actually, sometimes much better than the software. So if you could see it with your eyes when you move it around, then that was a detection. If you just don't see it, that means that that's not a detection.
And,
that,
when you guys did that, did you see any detection?
no,
Right.
not to 13 Jupiter masses. So that's our detection limit. If there is something fainter than that, we don't know.
Yeah, of course.
But
yeah.
not to 13, and we are pretty sure that there is nothing down to 13 Jupiter masses
Yeah.
on that region between 2 astronomical units and basically 12 astronomical units.
Now, this particular star, is this a solar star or is it a red
No, this
dwarf?
is an M5 star. So it's
Wow.
cooler than this is about. We are talking about 3,400, 3,000, about 3,000, between 3,000 and 4,000 Kelvin the surface temperature. So it's a red star.
Yeah,
It's not a solar.
It's only like 0.4, 0.5 solar masses.
Yes, at that, yeah, I think, I don't remember now the scaling between the, but it's of that order. It's a very low mass star, so.
Yeah.
Well, not the lowest mass, but it is still a star. No, it is still a star. It is not, yeah, it is a red dwarf.
Yeah.
It is not a brown dwarf, it is a red dwarf. So it still has fusion,
Yeah.
hydrogen fusion in its nucleus. So.
What about,
Yeah?
if you, stars that you know have been confirmed by radio velocity or the Kepler type line of sight transit, can you look at them and see, can you get an image of the planets, or you're not sensitive enough?
In fact, this is one of a program that has like 30 stars.
Okay.
That in which is a larger program. It's actually one of the warranty time programs for this instrument, which is trying to look. But think about this. We are looking at a completely different parameter space as Kepler is looking at. Okay.
Yeah.
Well, I was wondering if you could detect, say, the planets around Fomalhaut, which have been directly imaged.
I'm not so sure we tried that one. But we tried Sirius,
Right.
which has a companion, and we've detected that one, and we've tried some other ones that had. So we
Yeah, but
tried a
Sirius,
few.
that's a white dwarf companion, right?
Yeah, it's white.
No, but it has only a white dwarf companion. I should look at the table. I don't know. We've tried a
I
couple.
believe it is just a white dwarf. It's around
Yeah, yeah, yeah.
Sirius.
Sirius B is a white dwarf.
Yeah.
Yeah.
I think it was
And
the
is
first
there-
one discovered too.
Okay, so we've looked at I know that we've looked at several that a few that have detections, and we've been able to detect the detections that were already there. Okay.
Okay.
So, I don't remember now the.
Yeah, but that's another way of looking at it, so you get some new information.
Yeah, well,
Yes.
you verify the
Well,
instrument many ways.
Yeah, and it's a way as well of verifying that what you are doing is correct. So, but we are talking about massive planets at relatively long distances from the star. Okay, we are not talking about Earth mass planets close to the star.
Right.
This is a completely different business. And the last one is this is something that this instrument was not planned to do, but well, it happened that there was a
Oh, you mean
supernova.
with the supernova in M82?
Yeah.
Oh, yeah.
Oh, and what
So
did you
this is
discover?
actually okay. So I'm gonna show you something that is quite cool, because this is something that is the first time that is being done, and this is another paper that was published on that. So first, Canarican was never thought to be looking at supernovae, but this one happened in 2014, 2 years ago, in January. Actually, it was yes,
We all did, looked at it, took pictures, did everything.
and
Mag 10 is an easy reach of an amateur instrument.
yes, of course, that was 10th magnitude. In fact, the
Yeah,
peak was
yeah.
10th magnitude,
that's-
so
That was-
very easy
that
to
was
do. And this is
wonderful.
one visible image of it. So what we did was took a spectra in the mid-infrared. And one thing that you can do, this is really amazing. This is something that I never thought that you could do in the infrared. So basically, what you have here is the 10 micron spectrum of the supernova at day 57, the blue curve, day 81, day 108, and day 137, until it got too faint even in the infrared, and you couldn't do this anymore. So this is the spectrum of the supernova as a function of time, and you have here 3 different emission lines. We thought at the beginning that there was an error, because this didn't look at all as the spectrum of things that you are used to look at in the infrared. And you can see here argon 3, cobalt 2 and 3. The cobalt 3 is this brightest peak here, and you can really see how this evolves in time. And it turns out that this dot line that you see here are models of how the supernova gases evolve with time as the supernova spans. Okay, and you can try to match this and try to understand what processes are occurring there, and test. Basically, you can use these observations as a test bench for the models. And as you know, this is quite important, because type 1a supernovae
Yeah.
are standard candles.
Yeah.
So we are assuming that they are all they all get the same brightness when they explode, and that's why they are used as standard candles. But if you want to do what is called precision cosmology, maybe you have to start worrying about not being exactly the same brightness depending on which type of you know that the type 1a supernovae is a white dwarf, and then you have another star, and this another star can be anything. But what drives the brightness of the supernova is the fact that you have the white dwarf, which has relatively constant properties, no matter what the companion is. Okay, so you can start looking at these little details and see if really type 1a supernovae are standard candles or not. Okay, so that's one of the things that we also did with Canary Can, and the paper came out from this. I must say that in all these projects I've been involved more at the data reduction and data analysis than the science itself. You know, so it's because when you are a support astronomer, your way to get papers out is to say, okay, you know, I can reduce the data, and then if you do data reduction or something like that, they normally invite you as a collaborator for papers. Okay, so but then you learn a lot of stuff about what they do. I mean, it's really interesting. And it's a very it's three different.
Well, to be honest, you're of great value to the PI because you understand in doing the data reduction, you have to account for the instrumental peculiarities.
And you
know the instrument.
You are working with the instrument every day, so you really. Yeah, I mean, you really know what can be wrong and what is right, so that's basically the way you contribute to their science. And you are helping as well, which feels good. So, okay, and that was my last one, so it was a little bit long, and sorry about this, but this is the end of my presentation.
This is very informative. Very informative.
He only signed on for a 40-minute talk, and he's now been at it for like an hour and a half, so...
Well, I was told that this was quite flexible, wasn't it?
No, we appreciate
Well, nobody's
it.
gone stomping out of the room, so...
Right.
So,
It didn't
okay.
even feel like an hour and a half.
If you have questions, come on. I would be glad to ask.
Well,
if you are not too tired already, because I mean it's
Well,
late.
I didn't know about that you could from the ground do this type of infrared, so I didn't even know this could be done. I, of course, knew about near infrared,
Yes.
and of course, the space telescopes. But I didn't even know you guys could do this, so to me, this is incredibly fascinating.
It can be done. It can be done. As I said, this stuff is difficult, but it can be done.
So, do I understand correctly that CAC is also doing medium?
No, used to do it. So
Used to
cake.
do it,
So
okay.
this image that I was showing of this BN object, this demonstration image, this was from 2002. I don't remember when the LWS instrument was
It was
decommissioned,
before I
but
got here, so more
and
than
you-
10 years ago.
before than 10 years ago. So.
9 years the end of this month, so close enough. And they had stopped using the instrument sometime before I got here.
Okay.
So is there what's the latest update of what we might have a possible launch of the James Webb?
You mean in which terms?
Huh?
In which terms?
As far as I know, they're still holding to 2018.
Oh, you mean the date?
Yeah, the
I
date.
think they are doing pretty well. I mean, they are already mounting. If you go, I get the tweets from the James Webb page, and they are just mounting the segments. I mean, they are really
Yeah,
building
that I
it.
knew about.
They are really building it. So there is, I think they are more or less on time. So
That will be extremely exciting.
yes, and finger crossed for it to work.
Well, if it doesn't,
That's,
it.
It has to work, it has to work.
Thanks, Carlos. Thank you
Oh,
very
you
much.
are welcome.
Thank you.
Thank you. Sorry that it was so long.
By the
No,
way,
no,
the
we
name of the
didn't even
picture,
feel the time go, right?
Carlos,
A reminder that,
The name
as far
of
as I
the
know, we have
picture. Is the Heart of the Sea,
Warren from TMT for next month.
and it is the basis of the
Warren
novel
Skidmore.
Ah,
Moby
yes,
Dick.
for the next meeting.
Moby
Yes.
Dick was not fiction.
Thank you.
Moby it was not fiction.
No, it was
Well, it
a
was based
fiction
on some-
story about
based on the
Real
way
reality
the way
of